If you watched the previous video on 0th order rate laws, we said that any old reactant A becomes products, and we could write down two rate expressions for this reaction. From those two rate expressions, we derive this equation, where the negative change in concentration of A as a function of time is equal to a rate constant K times the concentration of A raised to some power n. In this video, we'll consider the case where n is equal to 1, and from this derive a first order integrated rate law. So, let's jump in. If n is equal to 1, our equation circled above becomes this expression. Negative change in concentration of A with respect to time is equal to rate constant K times the concentration of A. In order to solve this equation, we'll rearrange in such a way that we get like terms on the same side of our equation. What I'm going to do is multiply both sides by dt, divide both sides by concentration of A, and move the negative sign over just to simplify my life later on. This ends up giving me dA over just the concentration of A is equal to negative K dt. One more time, I'll integrate over the bounds from 0 to t on the right-hand side, and the corresponding concentrations, initial concentration of A at time 0 to concentration of A at time t on the left-hand side. Negative k is once again a constant, so we can take that out in front of the integral on the right-hand side. On the left-hand side, if you remember from your calculus class, that dx over x integrates as the natural log of x. We'll apply that same principle here. On the left-hand side of our equation, we end up with the natural log of the concentration of A integrated in the bounds from A0 to A at time t. On the right-hand side, we end up with a constant negative k multiplied by t integrated over the bounds from 0 to t. Plugging these things in and simplifying our equation down, we end up with an integrated first-order rate law. It looks like this. Another way to express this, again in order to derive a straight line relationship from it, is to move the entire term natural log of A at initial time 0 over to the right-hand side. An integrated rate law for first-order reaction looks like this. Once more, we can approximate this as a straight line. This time we have to be a little bit more creative though. This looks like a straight line if the entire term on the left-hand side is representative of our y-axis. The term negative k represents our slope, and the term time represents our x variable. Our y-intercept in this case, therefore, would be the entire term, the natural log of the concentration of A at time 0, our initial concentration. But once more, because we can approximate this relationship as a straight line with, albeit a little bit more convoluted metrics, we can plot on a horizontal axis time once again. This time on a vertical axis, though, for first-order integrated rate law, we'll plot the natural log of the concentration of A as a function of time. Notice, though, that once again, our concentration of A at time 0, even if we take the natural log of it, will be greater than 0. Perhaps we start somewhere up here along the vertical axis. And, furthermore, notice that our slope is negative, and that this relationship gives us a straight line that trends downward over time. The slope of this straight line is equal to the negative value of our rate constant k. So that, again, if only we knew what the slope of this relationship were, we could determine the rate constant for a first-order reaction. all first-order reactions will have a graph of the natural log of the concentration of A as a function of time, represented as a straight line, sloping downward.